Have you ever stopped to think about something as simple as a paperclip or a rubber band? I mean, you stretch a rubber band and it snaps right back. You bend a paperclip and it just stays bent. It seems obvious, but why? What's going on deep inside that material? Well, today we're going to dive into exactly that, the hidden rules that tell everything around us whether to bend or to bounce back. So this is the big question, right? It's our central mystery. And the answer really gets down to two fundamental ways that any material can change its shape when you push or pull on it. It's all about the difference between a temporary change and a permanent one. So here are the two big ideas. The temporary bounce back change is called elastic deformation. That's our rubber band or a spring. It has a memory of its old shape. But the permanent stay bent change, that's called plastic deformation. And that's our paperclip. It's forgotten what it used to look like. Once it's bent for good.
Okay, to really get a handle on this, let's zoom in on the simplest possible case of elastic behavior, a good old-fashioned spring. It turns out it follows this incredibly simple, really elegant rule that was figured out centuries ago, and it's basically the foundation for everything else we're going to talk about. So let's get a bit more formal for a second. Elastic deformation is that ability to recover its shape completely, and just as important, immediately after you let go. You can almost imagine the atoms inside being connected by tiny springs. When you pull them apart, they just can't wait to snap right back to where they started. And this brings us to the key principle discovered by Robert Hooke, Hooke's law. All it says is that the more you stretch something, the harder it tries to pull back. It's a perfectly straight line relationship. If you double the stretch, you double the force pulling back. Simple as that, but it's an incredibly powerful idea. In the language of math, it looks just like this. P is that restoring force, the thing pulling back. X is the displacement, how far you stretched it. That little negative sign is just there to remind us that the force is always pulling in the opposite direction of the stretch. But that letter K? That's where things get really interesting. This K is what we call the spring constant. It's just a number that tells you how stiff that specific object is. And here's a super important point. K isn't just about the material. It's about the object's shape too. How thick the wire is, how wide the coils are. Think about it. A slinky and a heavy-duty car suspension spring can both be made of steel, but they have wildly different K values, right? So Hooke's law is fantastic for talking about one specific spring. But what if we want to talk about materials in general? Like, how do we compare the fundamental properties of steel versus aluminum, no matter what shape they're in? Well, for that, engineers had to invent a whole new universal language. Yeah, that's the real challenge. We've got to find a way to move past talking about a single object's stiffness and start talking about the inherent stiffness of the material itself. We need a language that works for a tiny wire just as well as it does for a massive I-beam in a skyscraper. And the solution is actually pretty genius. We just normalize everything. We replace the specific idea of force with a universal concept called stress, and we do the same thing for displacement, turning it into a universal concept called strain. Let's break those two down real quick. Okay, so stress, that's the Greek letter sigma, isn't just about how much force you're applying. It's about how concentrated that force is. Here's the classic example. Think about someone standing on snow. If they wear snowshoes, their weight is spread out, so the stress is low. But if they wear a stiletto heel, that same force is concentrated on a tiny point, creating enormous stress. It's all about force per area. And strain is basically the same idea, but for stretching. Instead of just saying something stretched an inch, we ask, an inch compared to what? If a 10-inch rubber band stretches 1 inch, that's a huge amount of strain. But if a 100-foot steel cable stretches 1 inch, the strain is absolutely tiny. By making it a ratio, we get a universal way to talk about deformation. Okay, so now we have our universal language. Stress and strain. We can now describe what's happening inside any material under a load. And this lets us pinpoint the most dramatic moment in any material's life. That critical point where it stops bouncing back and starts to bend for good. The point of no return. The way engineers visualize this whole story is on a graph called the stress-strain curve. Think of it like a biography for a material. On the vertical axis, we plot the stress, how much internal force it's feeling. And on the horizontal, we plot the strain, how much it's deforming. This one graph tells you basically everything you need to know about how that material will behave. So the story always starts the same way, with a straight line. When you first start pulling on a material, it behaves perfectly. The stress is directly proportional to the strain. Hey, that's just our old friend Hooke's law, but in our new universal language. And this perfect, predictable behavior continues up to a point we call the proportional limit.
And right near that point is the most important landmark on the whole map, the elastic limit. This is the moment of truth. It's the absolute maximum stress the material can handle and still snap back to its original shape. If you go 1 ounce of stress beyond this point, the material is changed forever. The second you cross that elastic limit, the material yields. You've now entered the land of plastic deformation. The change is permanent. This is the exact moment our paperclip stopped acting like a spring and just became a bent piece of metal. It has no memory of its original shape anymore. All right, so we've seen how materials behave elastically, and we know about the point of no return where they deform plastically. But what if we could take that entire elastic behavior, that whole straight line part of the story, and boil it down to just a single powerful number? A number that defines the true inherent stiffness of a material. Well, we can. That number is called Young's modulus, or the modulus of elasticity, and we label it with a capital E. This is one of the most fundamental properties of any material. It's the number that tells an engineer how much steel will resist stretching compared to aluminum or plastic. It's the material's stiffness signature. And look at this. It all comes together in one beautifully simple equation. Remember Hooke's law for a spring? Well, think of this as the grown-up, universal version for any material. Stress equals Young's modulus times strain. As long as you stay within that elastic limit, this law tells you exactly what will happen. So if you look back at that stress-strain curve, Young's modulus is nothing more than the slope, the steepness of that initial straight line. That's all it is. A really steep slope means a high E. That's a super stiff material, like steel. A much shallower slope means a low E. That's a more flexible material, like nylon or rubber. It's all right there in the shape of the graph. And that's really the big takeaway here. This language of elastic and plastic, of stress and strain, and of a material's unique stiffness signature, E, this is what lets us build our world. It's how we design everything from a skyscraper that sways in the wind to a jet engine that holds together under incredible force. It's how we know with absolute certainty if something is going to bend or if it's going to bounce back.